Welcome to Chapter 5, which is all about exponential functions. Today we're starting with exercise 5a, which is exponential functions. And what we're going to be doing is learning about the graphs of exponential functions. And just like with any graph, we want to be able to know about the special features. So in this case, that would be the horizontal asymptote. We want to be able to apply any transformations, find the intercepts, and finally be able to sketch our graphs. So you would have already learnt this last year, but this is the graph of an exponential function. It looks like this function here. We've got a base to the power of x, and of course these are different types of transformations. So h moves it left and right, k moves it up and down. Now you'll have notice that we have an asymptote in this case at y equals to 0. Why do we have an asymptote? Well, if we think of our exponential function, say we take 2 to the power of x, we can start to think about what happens as x gets larger and larger, so as x approaches infinity. Well, if I put 2 to a very large number, so 2 to a very large number, all that's going to happen is that this value is going to get larger as well. So 2 to the power of 5, 2 to the power of 10, 2 to the power of a million, you could imagine is going to get closer and closer to infinity. So that's why as x gets larger, y also gets larger. But then our next question is, what happens as x approaches negative infinity? So what happens as our values go this way? Well, if we have a negative number, so say it's 2 to the power of negative whatever it might be, so I'm just going to call it negative a, well, what does that negative do? In fact, that makes it a fraction. So as we're getting closer to negative infinity, that means 1 over 2 to the power of a very large number. Well, to the power of a very large number, this is going to become very large, but 1 divided by a very large number will actually be very close to 0. It'll never actually be 0, but it'll be like 0.00000 closer to 0. So it will never be 0, but what happens is it gets closer to 0. So a bunch of zeros and then ends with a 1. So what we will say is that as x approaches negative infinity, y is going to approach 0. And that arrow there should be the other way around. So that's why we have an asymptote. We say that y approaches 0, never that y equals 0. So that's just a little bit of a background information about our exponential function. So in terms of the base itself, all of the functions are going to behave the same, but the base is just going to affect how steep the graph is going to be. So you could imagine if I have 2 to the power of 2, which is 4, compared to 10 to the power of 2, which is 100, then our graphs are going to be very different. So at 2, we want all the way to 100 compared to here, which would just be 4. So you can see that our graphs just grow steeper as our base changes. So what we're going to now do is apply our first type of transformations, which are reflections. So if we have a look at part A, exactly what we've done in our last topic, when the negative is on the inside, that's going to be a reflection in the y-axis. So we'll draw up a nice axis here. And this is for part A. Now, normally our graph is going to do this. And the way to think about it is that as x gets larger, y also got larger. This time, negative x, so if I input a negative number in here, the negatives become a positive. So it's going to behave the opposite way. So that's why there's going to be a reflection in the y-axis. So it's going to look like this. Now, our y-intercept, if I make x equal to 0, that's just going to be 1. It will always be 1 unless there's a translation, because anything to the power of 0 is 1. And our asymptote remains as it is at y is equal to 0. So that's part A. Part B, so we have negative 2x. We know that this negative is a reflection in the x-axis. So we've already worked out our values, and now we just want the negative version of it. So again, if we try to draw a little graph of what our original looks like, now we're going to reflect that in the x-axis. So it'll look like this. Now before my y-intercept, whoops, it's gone linear. Before my y-intercept was at 1, now that we have a reflection, well, it's going to change to negative 1. In fact, it's probably better to write it as a whole coordinate, like this. Our asymptote, however, stays as it is, so y is equal to 0. Finally, for part C, you can see that we've got a reflection in both the x and the y-axis. So again, I'm going to draw up myself a nice pair of axes. Original graph looks like this. We've got a reflection in the y and then a reflection in the x. So it'll look like this. And there's all of our graphs with different reflections. So just as a little bit of a summary, I've got some slides with them on. So here's y equals 2x, that's our original. This is a reflection in the x-axis, reflection in the y-axis, and a reflection in both. So now we're going to move on to our other type of transformation, which are translations. So in this case, all that's happened is that the whole graph has moved up by 1. Of course, we can also see that there is a reflection in the x-axis. So we might quickly, there's reflection in the y-axis because it's on the inside, and then we move up by 1. So it's always useful to write out our little transformations. X, Y. Now, what does it mean that the whole graph has moved up by 1? Well, my original graph or my original asymptote was at y equals 0, but now that the whole graph has moved up by 1, now our new asymptote is going to be at y equals 1. That's always a really good place to start. So that'll be y equals 1, and then we've got a reflection in the y-axis. So previously my y-intercept was at 1, but because I've moved the whole graph up by 1, then that will be at 2. And we can check that by substituting in 0. So 2 to the power of 0 is 1, and 1 plus 1 is 2. Part A, something very similar, for part B. This time we can see that we've got a reflection in the x-axis, so that's that negative on the outside, and secondly, our whole graph has shifted down by 1. Again, what that's going to do is affect my asymptote. Now my asymptote is going to be at y is equal to negative 1. So once again, I'm going to draw up my axes. And a reflection in the x-axis. Previously it looked like this, and now it's going to look like this. If I had reflected it, the y-intercept would be at negative 1, but I've moved it down again, so now it looks like it'll be at negative 2. But again, we can check, so that'll be, it's all negative, so that's negative 1 minus 1 will be 2. Example 3, sketch the graph of y equals, or f of x is equal to 2x minus 1 minus 2, showing the intercepts and asymptotes, stating the domain and the range. So there's lots of things that we have to do. So first of all, we need to sketch, but in order to sketch, we need to make sure we've also got our intercepts and asymptotes. So I might put 2 for both of those. And we also want to make sure we state the domain and range. So I just like to label them so that I can make sure that I am going to end up doing all of the steps. Now, to sketch the graph, we can do a rough sketch, but finding the intercepts will definitely help us in terms of where the graph is going to go. But we can just start by looking at what transformations have happened. So we've got the graph of y is equal to 2x minus 1 minus 2. There's been no reflections, but we've got a horizontal translation in the positive direction by 1. So remember, these have got little brackets and our sign is changes, and then we've moved down by negative 2. Now, moving our graph across this way isn't actually going to do too much to what it looks like, because it already looks like this. Like, moving it across isn't going to do too much. Of course, moving it up and down makes the biggest difference. So moving it down by negative 2 means that our new asymptote is going to be at negative 2. So we can start to already draw our graph and see what kind of a difference it's going to make. So what you'll notice is that if you go ahead to draw this graph, because there's been no reflections, we come across a little bit of an issue. We know the shape. The shape is going to look like this, but the problem is it going to go through this part, or is it going to go through this part? The only way to know is to be able to find our intercepts to help us out with that. So let's go ahead and do this. So for our intercepts, we'll start with our x-intercept. So that means we'll make y equal to 0. So that'll be 0 equals 2x minus 1 minus 2. If I take the 2 over, that'll be 2 equals 2x minus 1. Now this 2 is to the power of 1, and because the bases are the same, that means 1 is equal to x minus 1. That means x must be equal to, if I take it over, 2. So here, because the bases are the same, I can compare the powers. Now that's for the x-intercept. As for the y-intercept, I'm going to make x equal to 0. So that'll be 2, 0 minus 1 minus 2. 2 to the power of negative 1 is a half minus 2. And then a half minus 2 is going to be negative 3 on 2. So now very clearly I can see that my x-intercept is positive and my y-intercept is negative. So it's going to move through these 2 points. Now that I have this information, I can go ahead and draw a line through them. Now we've sketched the graph and we've shown the intercepts and the asymptotes, so that's all well and good. We've just got our last part where we need to show our domain and our range. Our domain for exponential functions is quite straightforward. It's just all real values, negative infinity to infinity. So we can say x is an element of all real values. For our range, however, it's not going to be all real values. As you can see, the smallest value is negative 2, but not included. And then our highest value will be infinity, also not included. So now we have completed our domain and range. Example 4, sketch the graph of f of x is equal to 2 minus 3x, 2 minus 3 to the power of x minus 1, showing intercepts and asymptotes and stating the domain and the range. So same thing again, sketch the graph, show intercepts and asymptotes, state the domain and the range. And the first one is showing all of your workings, and then we're going to practice this on the CAS calculator as well. So you might want to pause the video here and try it yourself, and I'm going to go ahead and do it so you can check your answer along with it. So the first thing I'm going to do in terms of sketching is I'm going to figure out what transformations have happened. So we've got a reflection in the x-axis. So that's this negative here. I might just label them. I know there's lots of 1s and 2s going on, but that's 1. And then I've got the graph is going to move to the right by 1. Again, it's not going to look that obvious. And so that's 2. And then 3, the whole graph is going to move up by 2. Of course, this means that my asymptote is going to be at y is equal to 2. From there, we have enough information to go ahead and sketch. That's a bit funny. I don't know why I did that. All right, so our asymptote is at y equals to 2. I might just bring this down a little bit, although there is a reflection. I might just leave it as it is. Y is equal to 2 is here, and normally my graph looks like this. However, there is going to be a reflection. Again, we have the exact same issue as before. We don't know whether it's going to look like this or this. So before we go ahead and sketch, we should find our intercepts to help us. So x-intercept, make y equal to 0. 0 equals 2 minus 3x minus 1. I'm going to take this over this time. Now, in this case, we come to a situation where we can't compare the bases. So if you remember this from last year, that's great. If not, don't stress too much about it right now because we are going to learn it in a few lessons' time. But the way to get to 3 over is to take the log 3 of both sides. So that'll be log 3, 2. And then that's log 3, 2 plus 1. But again, don't worry too much if you don't know it. Now, the only annoying thing with this, I mean, it looks like it's going to be positive, but sometimes it ends up being a negative number. So we will need to find our y-intercept to really help us ground where it's going to be on the axis. So for our y-intercept, now we're going to make x equal to 0. So that'll be 2 minus 3 to the power of negative 1. 3 to the power of negative 1 is a third. So then 2 minus a third. 3 times 2 is 6, minus 1 is 5 on 3. So we can see that the y is positive as well. So what I can do in this case, I'm just going to draw my graph with the reflection. So normal graph like this, reflected in the x, with positive x and y intercepts, and then sort of wherever it lands, I can say that's where my intercepts are. Again, don't worry too much if you don't remember the logs. We'll be looking at that in a few lessons' time. Now that's my graph. In terms of the domain and the range, very similar to before. The domain is going to be every real value, so x is an element of every real value. And the range, this one's going to be a little bit different. The smallest y value this time I can see is negative infinity, and then the largest is 2, but it's going to be not included. Now what we're going to do is we're going to complete this using our CAS. So if you can pull out your CAS. My CAS looks a little bit different to what yours does, but it's going to be the same idea. So we're going to add a new graph page, and then we're going to type in our graph. So that's 2 minus 3 to the power of x minus 1. And we'll press enter. So you can see that looks very much like what we did. To find the intercepts, so I want to go to analyze graph. 0 will help me find my, 0 will help me find my x-intercept. You can see this time it's not in exact values, so I'll show you how to find it in exact if that's what you need. But that's the decimal. And then to be able to find the y-intercept, we can go to graph trace, and usually it'll land on the y-intercept. If you just type in a number, if you just start typing in 0, it'll automatically take you to that spot as well. And you can see in the corner there it says 1.67, which is 513. Now, if you did want to find it in terms of exact values, what you can do is go to your calculator page and you can solve. So if I go to algebra solve, I've already got it defined now as f1 of x because I've just typed it in. So I can go f1 of x equals to 0, x and press enter. It's actually given us a little bit of a funny answer. So that's what it would look like in exact value according to the calculator, because it doesn't really calculate in terms of a log 3. But ln means log e. Again, it's something that we're going to learn later on. So to be honest, probably just discard this little part of the lesson. We'll look at finding exact values shortly. All right, so that's how you graph it with the CAS. We've got just a little bit more to go. So example 5, sketch this function over the implied domain and state the range. So again, we've got a bunch of different transformations that are going on. This time, what we have is this 6 times. So I know it looks a little bit weird, but all that's happening is that this is a dilation. And again, dilations don't really matter too much in terms of what it's going to look like overall, unless we're comparing graphs. So yes, the base changes how steep it is, but the dilation also changes how steep it is. So in terms of our transformations, we've got 1, 2, 3, if we sort of write them out. So transformation 1, we've got a dilation of factor 6 from the x-axis. Then I've got, we're moving to the right by a factor of 1. Again, doesn't really affect much. And then we're going to move down by 12. This one is very important because that's going to be my my asymptote. There's no reflections, so hopefully this graph should be straightforward to graph. And because there's a dilation, I mean, it looks like our graph should do this, but there is always a chance that it's going to do this. So once again, as always, we need to find our intercepts first. So let's go ahead and do that. I'm going to take the 12 over and then divide by 6. So that's going to give me 2 equals 2x minus 1. And this is really nice because I can see that 1 equals x minus 1. Take that over, that's 2 equals x. So that is beautiful. I already know that it's going to go through here now. So that'll be 2 and 0. And then I can find my y-intercept by making x equal to 0. 0 minus 1 is negative 1. So 2 to the power of negative 1 is a half, and a half times 6 is 3. So 3 minus 12 will be negative 9. So that's going to be the y-intercept. In terms of the domain and range, as always, domain x is every real value, and range, well, our smallest y value is negative 12, and that goes all the way up to infinity. And that's the end of exercise 5A.